The next talk is about improved quantum rebound attacks on double block length hashing with round reduced AES-256 and area 256. The work by Dongja Lee and Seok Hon, and Dongja will give the talk.
Thanks for the instruction. Hello everyone. This is Dongja Lee from Gangwon National University. And the title of my presentation is Improved Quantum Rebound Attacks on the Block Length Hashing with Round Reduced AES and ARIA. And this is the joint work with Seok Hong. As you can see in the title, our work is about quantum rebound attack, looking at related works. Rebound attack is differential cryptanalysis-based hash collision attack proposed in 2009. And later, in 2020, quantum rebound attack was proposed, and it was first dedicated quantum collision attack. And this work showed that a differential trail, which was infeasible in the classical setting, can become usable in the quantum setting. So following this research, many variants of quantum rebound attack one is quantum rebound attack on HCF AES, and the other is the quantum rebound attacks on HCF ARIA, where HCF refers to Hero's S double block length compression function. Will flows in these two previous works. The flows arise due to slight differences in solving the S-box differential equation in classical and quantum settings. However, we were not the first to notice this difference, and there are already methods to address it. So the real issue is that if the existing methods are used to address the flows, so to improve the quantum rebound attack, we use nested quantum amplitude amplification, pre-filtering search space, and quantum state preparation. So as a result, we make the attacks more efficient than generic attacks again. So to explain our work in more detail, let's take a closer look at the rebound attack. Rebound attacks can be applied to structures where collision finding is reducible to finding a pair that satisfy the differential trail. And our target, Hero's S double block length compression function, is one such example, but I will omit the explanation why this is the case in this presentation. And the rebound attack find the pairs that satisfy the entire differential trail as follows. It first find many pairs that satisfy the inbound phase trail, which we call starting points. And then starting points are propagated through outbound phases to find the collision. And so the remaining questions are how many pairs need to be found in the inbound phase and how to find these pairs in the inbound phase. So for the first question, the answer is P inverse, where P is the probability that a pair follows the outbound phase and the entire differential trail. And for the second question, while this is dedicated for the target, it generally follows the process outlined below. We enumerate the input and output differences of the inbound phase, delta in and delta out. Next, we propagate these differences inward until they meet at a nonlinear step, like so bytes. Finally, solve the S-box differential equations and propagate the values outward. So since the S-box differential equation has on average one solution, we need to enumerate P inverse pairs of delta in and delta out. And as a result, the overall complexity of rebound attack is roughly P inverse multiplied by the sum of cost for inbound and outbound phases. So for quantum rebound attack, uh, it defines this entire process as a function f, and this function f takes delta in and delta out as input and outputs 1 if these delta in and delta out produce a collision after inbound phase and outbound phase. So then we construct a quantum gate for UF, uh, quantum gate UF for this function f, and find the input for f that outputs 1 using Grover search. Grover search is a quantum algorithm for unstructured search, and given an n-bit input, uh, it works on a function that outputs either 0 or 1, and the goal is to find an input that outputs 1. In the classical setting, this requires 2 to n evaluation of functions, but in quantum setting, Grover search, the overall complexity of quantum rebound attack is roughly the square root of P inverse multiplied by the cost for UF gate. But however, we have to consider one more factor. We need to carefully handle steps that are straightforward in classical setting, but non-trivial in the quantum setting. To clarify which step requires special handling, we represent the rebound attack as pseudocode. We enumerate delta in and delta out, solve S-box differential equations, and only if there is no solution, we immediately move on to the next value, and otherwise we enumerate all possible solutions. So for quantum rebound attack, we translate each operation into quantum setting, but the continue operation cannot be trivially adapted to quantum setting. This is because in global search, the wrong values cannot be discarded immediately. Instead, their amplitudes are reduced gradually over iteration. So the existing method address this issue by introducing auxiliary bits alpha. So if there are n S-box differential equation in attack, then we use n bit alpha, and each bit of alpha determines whether first or second solution for each S-box differential equation. So as a result, this increase the over complexity by a factor of the square root of 2 to n. And closing. So let's examine the attack on HCF AES. It is divided into two inbound phases with connecting part between them. To abstract the process, we enumerate input-output differences for each inbound phase, and propagate these differences inward until they meet a nonlinear step, solve S-box differential equations, and propagate the value outward. So note that we need to solve 32 S-box differential equations for this process. And finally, we find some internal values to connect two inbound phases. So The quantum rebound attack on HCF AES solves 32 S-box differential equations in their attack, making the correct complexity 2 to 16 times larger than their proposed complexity. Similarly, for the quantum rebound attack on HCF ARIA, the correct complexity is 2 to 19.5 times larger than their proposed. And as a result, some attacks in both works become less efficient than generic attacks. Now I will explain how to improve quantum rebound attack. And the first algorithm we use is nested quantum amplitude amplification. The QAA is generalized version of Grover search, and nested QAA utilizes the fact that support more complex searches. So to apply nested QAA to quantum rebound attack, we first generate a superposition consisting only of states that make the S-box differential equation to have solutions. Then we proceed with the remaining steps. So to do this, we construct the quantum gate for solution checking and use this gate for the first QAA. Some state consisting of only states that have solution remains after the first QAA. We then concatenate the quantum states for alpha and proceed with the remaining steps. And as a result, we can reduce the complexity by the difference between cost for UF gate and the cost for solution checking gate. Next, we apply pre-filtering. Suppose that we can efficiently pre-filter search space for delta in and delta out. In other words, suppose we have pre-filtering quantum gates such that generates a superposition that excludes some, not all, states that do not have solutions. Specifically, instead of starting with the superposition of all possible states, all possible states generated by Hadamard gate, we begin with the quantum state generated by pre-filtering gate, which excludes some states. And this reduces the number of iterations required for the first QAA. And as a result, we can reduce the coefficient in the complexity. So this is the overall complexity of our improved QRA, quantum rebound attack. And depending on the dominant factor, is split into two cases. First case is quantum rebound attack on HCF AES correspond to the first case, and quantum rebound attack on HCF ARIA correspond to the other case. So in quantum rebound attack on HCF AES, P inverse equals 2 to 160, but the number of active bytes is 24. So we can fix the values for 4 active bytes. And if we fix the values for 2 active bytes in inbound phase 1, as shown below, we can fix the values for orange bytes, and we can filter out half of values for each blue bytes shown in the figure. So, and the same approach can be applied to inbound phase 2. So to construct pre-filtering gate, we use quantum state preparation, which refers to methods for generating arbitrary quantum states. And for the blue bytes, as we saw earlier, we use state preparation to generate a superposition that excludes impossible values. And for other active bytes, we use Hadamard gate to generate a superposition, completing the pre-filtering gate. And this is the result of our work. So we improved the quantum rebound attack on HCF AES by a factor of 2 to 11.2. And we improved the quantum rebound attack on HCF ARIA by a factor of 2 to 19.5. So this table summarizes our research. And this is the end of my presentation. Thanks for your attention.
Thank you for the talk. Do we have questions from the audience? So this work is about the collision resistance of the compression function, right?
Yes.
Yes.
It defines collision.
Collision. And I wonder if you have some insight on the collision resistance of the hash function instead of the compression function.
That's the target is a compression function.
Yeah. Do you have some comment on the hash function? Any applicability or?
So our method is not limited to this case, but the condition for application is not. I think that is not general. So I didn't think that we. I don't even study more about the application.
Okay. Okay. Any more questions from the audience? Not. Let's thanks the speaker again.
Thank you.